This presentation is delivered by the Stanford Center for Professional Development.
Okay, back to numerical linear algebra, whirlwind tour. So last time we got as far as the LU factorization, which is also, I mean, it's the same as Gaussian elimination. So this is Gaussian elimination. And it basically says this: any non-singular matrix you can factor as a permutation times a lower times an upper triangular matrix. Actually, this of course is highly non-unique. There's zillions of factorizations. But for the moment, we're not going to even cover why you'd pick one over another or something like that. That's a topic you would go into in detail and whole classes on this topic. But the point is that once you have effected this, once you've carried out this factorization, you solve AX equals B by essentially you factor and then you do back substitutions or forward and backward substitutions. And the very important point about that is that once you've factored a matrix, and the cost, if the matrix is dense and you're not going to exploit any structure, is n cubed. The back solves are n squared. And actually, what this now you know something that's not obvious at first sight. I mean, you just have to know how this is all done to really know this, because it's kind of shocking. It says basically the cost of solving two sets of linear equations with the same matrix is actually equal. I mean, more or less, you know, I mean, for all practical purposes, it's identical to the cost of solving one. Okay? And that's not obvious, I don't think. Because if someone walked up to you on the street and said, how much effort does it take to solve two sets of linear equations compared to how much it costs to solve one set of linear equations, I think a normal person would probably answer twice. That's wrong. The answer is the same. Okay? And that's for a factor solve method. There are other methods where the number is twice. It couldn't be any worse than twice, I suppose, right? But the point is, it's the same.
Could you just put the two as one system? Is that what you're saying? Like just to stack the...
Nope. That would make it much worse. If you stacked it like that, you'd have a 2n by 2n.
Yeah.
And 2n cubed, you'd be off by a factor of 8. So you'd be 8 times more.
So what was your argument for being 2 less than 2?
Back solve. One factor, 2 back solves. Okay. Now we're going to get to something very important. A lot of you probably haven't seen it. It's one of the most important topics, which I believe is basically not covered because it falls between the cracks. It's covered somewhere, deep into some class on the horrible fine details of numerical computing or something like that. I guess. I don't think it's well enough covered, at least from the people I hang out with. Not enough of them know about it. And it has to do with exploiting sparsity in numerical linear algebra. So if the matrix A is sparse, you can factor it as P1, LU, P2. Now here you're doing both row and column permutations. And you might ask, I mean, you don't need the P2. For the existence of the factorization, all you need, in fact, is the existence of P1. You need P1 because there are matrices that don't have an LU factorization. So the P2 here really means that there's lots and lots of possible factorizations. And the question is, why would you choose one over another? And I'll mention just two reasons. Again, I'm compressing 6 weeks of a class into 60 seconds. But one reason is this: you would choose the permutations, the row and column permutations in your factorization. First, you choose it so that when you actually carry out the factorization, it's less sensitive to numerical round-off errors because you're doing all this calculation in floating point arithmetic, right? Actually, by the way, if you're doing this symbolically, then you don't need to. This first issue doesn't hold. But of course, 99.99999% of all numerical computing is in doubles, IEEE floating points. Okay. Now, there's another reason, and this is very, very important. It turns out that when you change the permutations, row and column permutations, the sparsity of L and U is affected. And in fact, it can be dramatically affected. So if you actually get the row and column orderings correctly, that's these two permutations, the LU that you will get here, the number of non-zeros in them when they're sparse. By the way, I should add something like this, that once P1 and P2 are fixed, and you normalize L or U by saying, for example, the diagonal entries of either L or U are 1, then this becomes unique, the factorization at that point. Otherwise, there's some stupid things you could do, like, for example, multiply L by 2 and divide U by 2. But once then they become a canonical form. They're fixed. And so once you pick these, there's only one choice for L and U once you normalize either L or U. So in fact, the sparsity pattern will be determined by P1 and P2 here. And if these are chosen correctly, you will have a number of non-zeros in L and U that is small. If you choose them poorly, it'll just be enormous. And this is the key to solving, for example, a 100,000 variable, 100,000 equation problem, AX equals B. You know, obviously, you can't remotely do that if it were dense. You can't even store such a matrix, okay, period. Okay? And if you could store it, I mean, I guess if you could store it, and I mean, theoretically you could, but it's a big deal, and you'd have to use a whole lot of your friends' machines and all sorts of other stuff to do this. I mean, it's a big deal to do something like that. However, if that 100,000 by 100,000 matrix is sparse, let's say, for example, it has 10 million non-zeros entries, which means roughly, this is all very rough, if you have 100,000 by 100,000, you have 10 million things. It means you have about 100 on average, 100 non-zeros per row and 100 non-zeros per column, just roughly. Well, I guess that's not rough, that's exact. But when you say average. So what that means is something like this. It says that each variable only enters into, on average, each of your 100,000 variables enters into, on average, 100 equations. Each equation involves, on average, 100 variables. Now, by the way, if you think that's an easy problem to solve, it's not. So, I mean, however, that can be solved extremely fast. Extremely fast if P1 and P2 can be found so that these factors actually have a reasonable number of non-zeros. If you start with 10 million non-zeros, if the L and U, if you're lucky, L and U will have about, 10, on the order of 10 million, 20 million on a bad day. 30 million would be fine. You're still no problem, just not even close to a problem. If you can't find P1 and P2 that end up with a sparse L, then it's all over. But in many cases, there's going to be very simple, shockingly simple and naive algorithms will find permutations that give you a good sparse factorization. Yeah.
How do you know if we're finding P1 and P2 whether it can be made sparse?
You don't know. So what you do is you run. Depends what you're doing. You run, you'll actually attempt to solve it, and then you'll be told. I mean, it depends, but actually it'd be really simple if it just doesn't respond, like for the next, and you can look at your memory allocation and watch it go up and up and up and up. Then you'll know it's not working. But it's easy enough to know ahead of time. There's actually 2 passes. I'll talk about that in a minute. The first pass is called a symbolic factorization. In the symbolic factorization, you only look at the sparsity pattern of A. And you actually attempt to find P1 and P2. In real systems, what would happen is this. The symbolic factorization would run, and by the time it's gotten to some upper limit, like 100 million or a billion, let's say, it depends on, of course, what machine you're doing this on. But after it gets to a billion, it might quit and just say, there's no point moving forward because the L and U I'm finding already have 100 million entries, something like that. So that's how you do it in the real. There'd be two phases for that. That's how it really works. The way that would work in MATLAB, which again, let me emphasize, MATLAB has nothing to do with the numerics. It's all done by stuff written by other people. They would just, I think, stop. I mean, you just write A\B, and it just wouldn't respond, and that would be its way of telling you that it's not finding a very good permutation. I'll say more about this in a minute. One thing that's going to come up a lot for us is Cholesky factorization. Not surprising. So that's when you factor a positive definite matrix. So if you factor a positive definite matrix, you can write it as LL transpose, L transpose. I mean, obviously what this means is it's an LU factorization. 2 things about it. You do not need a permutation. Every positive definite matrix has an LU factorization. In fact, it's got an LU factorization with L equals U. By the way, just to warn you, there's different styles for this. Other people, in fact, use, this is lower triangular. You can also do it as, I guess, let's see, upper triangular. There's an upper triangular factor. There's different ones, so you just have to check. In fact, let's see, who has recently used, what's the Chol? in LAPACK. That would be the standard. What does it return?
U?
An upper triangular? Oh, okay. So, sorry, we're backwards from the world standard. The world standard would be upper triangular, but everything works this way. So, this is the Cholesky factorization. It's unique. So there's a unique, and by the way, there's no mystery to these factorizations. I'm not going to talk about how they're done, but there's absolutely no mystery. I mean, you basically just write out the equations and equate coefficients. I mean, I don't want you to think there's some mysterious thing and you have to take this 10-week course to learn what a Cholesky factorization. It's really quite trivial. To write down what it is, the formula for it is extremely simple. What you should know after our discussion last time of multiplying two matrices is the little formula we write down, that's not how it's done. It's done by blocked and hierarchies and all that kind of stuff, which exploit memory, data flow, and things like that. So let me just show you what I mean here. If you write A11, A12, you know what? That's good enough. A22, something like that. You simply write this out, that this is L11, L21, L22, times the transpose of that, which is L11, L21, and then L22, like that. And now, this is the Cholesky factorization. And you just want to find out, what are these numbers? Well, okay, let's start here. Let's take the 1, 1 entry. We notice that this times that is, so we find L1 squared is A11. Everybody following this? So obviously, L11 is square root A11. Okay, that's the first one. Now that you know what L11 is, you just do the same thing. You back substitute, and you look at the next row would be this one times this one would be L11 L12 equals A12. And now you divide out. Do I have to do this? I don't think I have to. I mean, this is totally elementary. You just write it all out. And so the existence and formulas, in fact, lots of formulas, obviously all equivalent for the Cholesky factorization, you can derive this way. But and then you could write, by the way, a little chol in C, and it would be about 5 lines. Again, like matrix multiply. But your chol would be beaten like crazy by the real ones, which would block it up into little blocks optimized for your register sizes and caches and things like that. Okay. All right, so that's the Cholesky factorization. So the way you solve, and here you get 1/3, and this is kind of predicted. The factor of 2 is totally irrelevant in flop counts. As I mentioned last time, you can be off by a factor of 100 comparing real computation time versus flop count time. So 2 things with an equal number of flop counts, like for example, your amateur chol or your amateur matmult could be beat by a factor of 100 by one that does the right thing. So, and they have exactly equal number of flops. So, actually, it could be more than 100. You could arrange it very nastily to you'd arrange n to be just big enough to have a lot of like cache misses and things like that, and we could arrange for that number to be big, almost as big as we like. Okay, so when you do a Cholesky factorization, not surprisingly, A is symmetric. A basically has about half the number of entries as a non-symmetric matrix. So the fact that the work is half is hardly surprising. But again, the factor of 2 is totally irrelevant. Nothing can be less relevant. Okay. So this is how you do Cholesky factorization. And there is one thing I should say about this, which is good to know, and that is this. When you do a non-symmetric LU factorization, the P is chosen primarily so that numerical round-off does not end up killing you as you carry out this factorization. You end up factoring something, but the product of the things you factor are not equal to the original matrix or something like that. So your answer is totally wrong. So the P is chosen for that. Now that means that this P is often chosen actually at solve time. So when you have to look at the data in the matrix A to know whether you should do to carry out the. That's called pivoting, by the way. By the way, obviously, if you don't have to follow everything I'm saying, but it's important to know some of these things. By the way, that slows down a code, right? Because if it's got branches and things like that, and then if it's got to actually pivot and stuff like that, and you have data movement on a modern system, this can be very expensive. Okay, so.
Why did you say it has fewer elements in the positive definite case? It seems like they're the same size. Or
Yeah, they're the same size, yeah, but this is a general one, so you have to give n squared entries to tell you what it is. This is symmetric, so you really only have half the entries. Okay. Now, so here you would choose this, the p dynamically. So actually when you factor a specific matrix. Here you don't need it. And in fact, it's actually well known that just straight Cholesky factorization actually is quite fast. And actually, it's stable numerically. In other words, it's known that this is not going to lead to any horrible errors. This means, for example, if this is small, like 100 by 100, you get something that's very, very fast. And also, it's got a bounded run. I mean, it's got a bounded runtime. It will be very fast, right? Because there are no conditionals in it, for example. Okay. Now we're talking about sparse Cholesky factorization. That looks like this. Here, you of course preserve sparsity by permuting rows and columns. Okay. So, of course, any permutation you pick, if I can write it this way, P transpose A P equals LL transpose. So the other way to think of it is this: is you take A and you permute its rows and columns. You carry out a permutation of its rows and columns, the same one. Then you carry out a Cholesky factorization. By the way, it's absolutely unique, the Cholesky factorization, provided you normalize by saying that the diagonals are positive. Otherwise, it's a stupid thing. Question? No. Okay. Okay. So it says I can permute the A's any way I like, and then I compute the rows and columns of A and then carry out a Cholesky factorization. When A is sparse, this choice of P is absolutely critical. So if you give me a sparse matrix and I pick one P, there's just a Cholesky factorization, period. And that Cholesky factorization will have a number of non-zeros in L. In fact, if you choose P randomly, L will basically be dense for all practical purposes. Okay? And then it's all over. Especially if your matrix is 10,000 by 10,000, it's pretty much over at that point. Yeah?
Solving linear equation using Cholesky, you need to know if the matrix is positive definite, right?
That's correct. Right. So
what's the
I can tell you exactly how that works. So in some cases, it's positive definite because, for example, it's a set of normal equations. That's very common. Or it's going to be something we'll talk about later today. Maybe we'll get to it. Newton equations. Right. So a lot of times it's known. Now, in fact, the question is, what happens? Obviously, if a matrix has a Cholesky factorization, it's positive definite. In fact, if L is, especially if this is the case, it's positive definite. What happens if it's not? That's a good question. And here, I didn't get very far in my Cholesky factorization. But in fact, what would happen is this. At each step of a Cholesky factorization, there's a square root. Right? You see, we only did the first one. The next one would be square root of, that's basically the determinant. Okay, it'd be the square root of the determinant would be the next one. What will happen is this. That square root, if all those square roots, if the arguments passed to them are all positive, then you will have a Cholesky factorization. If that matrix is not positive definite, one of these square roots, you're going to take a square root of a negative number. Okay, and then several methods. There's actually different Cholesky factorizations modified. In fact, I forget the name of it, but there's a type of Cholesky factorization which you might want, and it works like this. Right before it takes a square root, it has a test that says if this thing is negative, it throws an exception. By the way, it can even be arranged to actually calculate a vector z for which z transpose az is negative, which of course is a certificate proving a is not positive, definite, or less than or equal to 0, whatever. So that would do that. That's one way. Unfortunately, a lot of the other ones, because these are built for speed, it'll just throw some horrible exception from a square root or something like that. So that's there's a modified. In fact, Cholesky is in fact the best way to check if a matrix is positive definite. Finite number, you don't calculate the Eig or anything like that. You run a Cholesky. You don't run a basic Cholesky, which will dump core, and then that would be your. Then you have a system call to find. Anyway, no, I'm joking. But the way it would work is this: you'd run with this modified Cholesky that, when it encounters a square root of a negative number, does the graceful thing, which is to return telling you Cholesky didn't succeed, which is basically saying not positive definite. So that's the best way to check. Okay, let's go back to this one, this permutation. Now, so here's the way this actually works, now I'll explain how it works. The permutation here is generally not chosen in Cholesky factorization. What I'm about to say is not quite true, but it's very close, and as a zeroth order statement, it's good enough. You don't choose the permutation in a sparse Cholesky factorization to enhance numerical properties of it. Now, technically, that's a lie, but to first order, it's pretty close to the truth. It's a perfectly good, to zeroth order. It's a good statement. You choose the P to get a sparse L. That's what you do. Okay, and what happens then is this. There's a whole. I mean, there's simple methods developed in the 70s where you would choose these P's. I mean, and they have names like approximate minimum degree. You know. Then they get very exotic. Then there'd be ones like the reverse Cuthill-McGee ordering. Then you can get to very exotic orderings. So that's all fine. That's all fine. But now I'll tell you, as most of you would be consumers of sparse matrix methods. In fact, you don't know it, but you have already been very extensive consumers of sparse matrix methods. Because when you take your little baby problem with 300 variables and CVX expands it, I don't know if you ever looked, but if you look, you'd find some innocent little problem you're solving with 10 assets or something like that. If you look at it, it'll all of a sudden say, solving this problem with 4,400 variables. Well, you trust me. Oh, systems of 40, when it says 27 iterations, I promise you, equations of the size 4,400 by 4,400 were solved, each iteration. Okay? You would have waited a whole long time if this wasn't being done by sparse matrix methods. Right? So you're already consumers, big time consumers of sparse matrix methods. What I want to say about this is that even very simple, by the way, all the things that you did, although it's in the solver, which I don't know the details of, the orderings were very simple ones. There are things like approximate minimum degree. I mean, just really simple. And for most sparsity patterns, these things, you know, obviously work fine. So that's what this is. Now, the exact value really depends in a complicated way on the size of the problem, the number of zeros and the sparsity pattern. So actually, it's interesting I want to distinguish the dense versus sparse. So let's actually talk about that. And I'll just talk, you know, on a laptop, little PC, something like that. Dense is like no problem. You can go up to like 3,000. I mean, just no problem. It'll scale something like n cubed. You already know that, and it'll just work. It'll start allocating more memory and start taking like a macroscopic time. But you know, it's just going to work. There's essentially no variance in the compute in the compute time. It's extremely reliable. It's going to work. You know, it's going to fail if the matrix you pass in is singular or nearly singular. But then you shouldn't have been solving that equation anyway. So you can hardly blame the algorithm for it. So these things, for all practical purposes, the time taken to solve a 3,000 by 3,000 equations, 3,000 variables, the time taken is just deterministic. By the way, at the microscopic level, that's a big lie, but it's good enough. And the reason it's a big lie is very simple. Actually, depending on that matrix, the data in that matrix, different orderings and pivoting is going to do. And if you have no pivoting, it might take less time or whatever. And you have a lot of pivoting and all that, it might take more. But it's absolutely second order, not there. Okay, so that's the deal with three. So there's no stress in solving a 3,000 by 3,000 system. Zero, absolutely zero. It just works. You know, you can say exactly how long it's going to take ahead of time, and that's how long it's going to take, period. Now you go to sparse. Now, well, it depends. There's actually two passes. It depends on the sparsity pattern. So let's go to a typical example, 50,000 by 50,000 matrix. So you want to solve Ax equals b, 50,000 by 50,000. Now, some people, you can make a small offering to the god of sparse matrix orderings. That some people say is effective. But the point is, there's no reason to believe that you can always solve 50,000 by 50,000 equations. Okay? And in fact, there's ones that you can't. And it just means that whatever sparse solver, whatever ordering method is being used, typically on your behalf. I mean, unless you do go into large problems. If you do large problems, you have to know all of this material, every detail. Okay? If you don't work on huge problems, then this is stuff you just have to vaguely be aware of on the periphery. Okay, so in this case, 50,000 by 50,000, there's a little bit of stress. You type A\B, it might come back like that. You'll know examples where it'll come back like that soon. Okay? Or it might just grind to a halt, and you can go and watch the memory being allocated and allocated and allocated, and it just, at some point, you'll put it out of its misery. So that's one. However, the interesting thing is this. Once that's done, if you do it in two steps, if you do a symbolic factorization first, you're going to know. You'll know. Then after that, it's for matrices of that sparsity pattern, it's absolutely fixed. Right. So this, by the way, has a lot of implications in applications. If you write general purpose software that has to solve AX equals B, where A is sparse, you don't know. Basically, you deal with it every time it's fresh. If I pass you an A matrix, the first thing you do is you do a symbolic factorization. You start going over it, and first you look at it and you go, well, it's sparse. All right, let's see what we can do with ordering. Then you do the ordering, you do the symbolic factorization. You know how many non-zeros you're going to be. At that point, if you wanted to, you could announce how long it's going to take to solve that problem. Because once you know the sparsity pattern of L, it's all over. You know everything. In fact, just the number of non-zeros is a good get. Question?
What is symbolic factorization?
Well, first of all, that's in the appendix, which you should read. So let's start with that.
Appendix B?
Yes, okay. Some people are saying it's Appendix B. It's one of the appendices. There's not too many. So a linear search through the appendices wouldn't, is feasible, I think. So it's one of the appendices where this is covered in more detail, but you have to understand even that is like condensing a 2-quarter sequence into 15 pages or something. So, okay. So the interesting thing is if you're going to solve a set of equations lots of times, like suppose you want to do medical imaging or you want to do control or estimation or some machine learning problem or something like that, but you have to keep solving the same problem with the same sparsity structure. At that point, actually, you could invest a giant pile of time into getting a good ordering. So it could take you could run, there's whole communities that do nothing but calculate ordering. You could actually calculate an ordering for 3 days. And when you get, by the way, if you get an ordering that works and has sparse Cholesky factor, it's no one's business how you got it. Right, like a lot of things. It's fine. So you could do that, and then it can be fast. So, okay. All right, well, that's enough. Oh, so let me just summarize this. For dense matrices, totally predictable how much time it is. Sparse, depends on the sparsity pattern, depends on the method you or whatever is solving this equation on your behalf is using to do the ordering. By the way, if it fails on MATLAB or something like that because it's using the simple approximate minimum degree, symmetric minimum degree, blah, blah, blah ordering, it could easily be that if you were to use a more sophisticated ordering, it would actually solve it. Just no problem, right? So, okay. On the other hand, it's too bad that the sparsity pattern plays a role in these methods. On the other hand, you know, hey, you want to solve 100,000 by 100,000 equations? You can't be too picky. You can't say, wow, that's really irritating. Sometimes I can do it and sometimes I can't. So anyway, all right, enough on that. And finally, one more factorization we'll look at is the LDL transpose. So this is just for a general symmetric matrix. Here, the factorization is this. There's a permutation. There's an L and an L transpose. In fact, they can have ones on the diagonal. In fact, you can't. What you do here is D is actually block. It's block diagonal, and the blocks are either 1 by 1 or 2 by 2. Is such a matrix easily inverted, by the way? If I give you a block matrix where the blocks are 1 by 1 or 2 by 2, can you solve, you know, dz equals y? Well, of course you can, right? Because you either are dividing or solving a 2 by 2 system. So, okay. And it's sort of the same story, so I think I won't go into that. Now we'll look at something that's actually everything we've looked at so far is just so you can get a very crude understanding of what happens. There's nothing for you to do so far, right? So in fact, most of this stuff is done in most systems. This is done for you. You call a sparse solver. You can do that in MATLAB just by making sure A is sparse and typing A\B, just for example. Or if the real thing would be to directly call something like from UMFPACK or spools, or there's all sorts of open source packages for doing this. And you're probably using them whether you know it or not. So you're certainly using it in MATLAB. If you use R, you're using it. Anyway, so actually I don't know. Does anyone know? Do you know what the sparse solver is and package in R?
R doesn't have one.
No, come on.
It's a separate package.
Then, okay, that's fine, but it has one, come on.
Yeah, but it's not like part of the core language.
That's okay. That's fine. That's I mean, come on, it's an open source thing. It doesn't matter then, right? So that's fine. Okay. Now we're going to talk about something that is going to involve your action. Everything so far is just me explaining what is done on your behalf by some of these systems. Now we're going to talk about something you actually need to know because you're going to need to do it. So, and these are things, by the way, that will not be done for you. They cannot be done for you. You'll have to do them yourself. So now is the time. Up till now was just sort of, here's how things work. Now you better listen, because now there's going to be stuff you have to understand and that you'll actually have to do. So we'll just start with this, just blocking out a set of equations. Really dumb. I mean, we just divide it up like this. You can divide it up any way you like. And we're just going to do elimination. So it's going to work like this. We'll take the first row, block row, says A11 x1 plus A12 x2 equals B1. So I solved that equation by multiplying on the left by A11 inverse, which I'm assuming is invertible. Obviously, a leading subblock of a non-singular matrix does not have to be non-singular, right? That's obvious, as in 0, 1, 1, 1 is obviously non-singular, and it's leading one by one block. It's A11 is certainly not. But assuming it is, you can eliminate x1, and you just get this. That's x1. You back substitute x1 into the second equation. And in the second equation, you get A21 x1. That's A21 A11 times this junk over here. And then that plus A22 x2 equals B2. And that equation looks like this. Now, this guy you have seen before, although you don't remember it probably, or maybe you do. That's the Schur complement. So Schur complement just comes up all the time. So you might as well get used to it because it comes up all the time. By the way, if you have an operator called the Schur complement, that's what the Cholesky factorization is, like 2 lines, because you just keep calculating a Schur complement of kind of what's below you or something like that. So that's the Schur complement times x2 is equal to this right-hand side. Now, so this suggests a method for solving this set of equations. And you do it this way. You first form A11 inverse A12 and A11 inverse B1. And by the way, I have to say something about this because this is sort of already high-level language. When you say form this, by the way, how do you do it? Do you actually calculate the inverse of A11? And it depends on what A11 is. So what this really means is the following. You factor A11 once, and you back solve for B1, and then each column of A12. Okay? So it's understood when you see this in pseudocode that you know what you're doing, and that you don't form this inverse and all that kind of stuff. It's just understood. That's what it means.
Implement that in MATLAB? Is there a good way to do that in MATLAB?
Yeah, there is.
Can MATLAB store that factorization somehow and reuse
Yeah,
it?
so this is coming up on your homework, which we'll put on the web server. That is, if it's up. Sorry about the AFS outage yesterday. I don't know how many people noticed it. 10? Anyone notice it yesterday? I think it raises our blood pressure a lot more than yours. So I got to learn actually just kind of, it's like a power outage, to just deal with it. But it makes me very nervous. That's my nightmare number 6, worst nightmare, is final exam, AFS outage. Or something like that. I don't know. Okay. What were we talking about? Back solving. Yeah, MATLAB. Yes, of course. Okay. Let's suppose that you needed to, let's suppose we're going to do a Cholesky factorization, Okay, so the way you do it is this. So you're going to factor a matrix A. Whoa. Okay, here's what you do. And this will work. So first I have to tell you a little bit about what backslash does. Okay, which you can figure out anyway. So it does a lot of things. I'll just give you what's essential for what we're talking about now. Here's what this does. First of all, it checks if A is sparse or something. But even if A is full, it looks to see if A is upper or lower triangular. Okay. If A is upper or lower triangular, actually more than that, if it can be permuted to upper or lower triangular, but let's say it's just if it's upper or lower triangular, it will actually do back solve. Okay, so for example, that means if I write A is 3000 by 3000, that's a big enough matrix that you will see a macroscopic difference. And I type A backslash B if A is full, it's going to take order n cubed. I don't know how long it'll take, 20 seconds, 15, 12, I don't know, something like that, okay? I mean, obviously depends on the machine you're on, right? But it's going to take a macroscopic amount of time. You'll hit carriage return, and you will wait a little bit before you get the answer, okay? If A is 3000 by 3000 and lower triangular, what will happen when I type A backslash B? Just, it's n squared, and it'll be, I won't even see it. I'll hit a carriage return. It'll take more time to actually go through all to interpret it and to instruct X or whatever's drawing your window to type into that terminal. That's going to take way more time than solving it. So it'll go from like 10 seconds to nothing. In fact, we can guess how much faster it'll be. It's going to be on the order of 3,000 times faster. That's by the order. But in fact, the numbers are different by a factor of 2, so it'll be about 1,000 times faster. This is my guess. Okay, so this is the first thing you need to know. Okay, now suppose you want to do suppose you want to solve AXI equals BI in MATLAB, where you have a bunch of these. Okay, so this would be intensely stupid. I mean, it should work, but anyway, that doesn't matter. If you did this, I'm just writing something that's in between. I don't even know what it is. But anyway, if you did this here, this thing, what do you think it'll do? It'll look at A fresh each time and go, great, let's factor that guy, right? It'll even recalculate the permutations fresh every time. Okay, so this is not the way to do it. Okay, if you do this though, it will actually do the right thing. If you do that, it'll do it. I mean, this is nothing but a batch. That's a batch solve. That's all it is. Because the columns of A inverse B, where B is this thing, is nothing but A inverse B1, A inverse B2, and so on. So you can call this a batch solve or whatever you want. So if you write A backslash B, it'll do the right thing. It'll factorize A once, and it'll go through the columns and back solve. Actually, to tell you the truth, even that is not correct. That's actually not what it does. But let's pretend that's what it does. It doesn't do that. It again blocks it out and calls an LAPACK code. But these are fine details. This will do the right thing here. Okay. So for example, what is the runtime of this versus this? What's the runtime of those two? Identical. Basically identical. It's not identical, but it's identical. Basically, it's the same for all practical purposes. Okay? So that's an important thing to know. Now we can put all these together. And now suppose you need to factor A once, but then you don't have all the things you want to back solve at the same time. Then you can't do this trick. It's not a trick, I mean. Okay, so here's what you do. Now we'll get to it and I'll show you how to do it. You would do something like this. I'm just going to do this approximately. By the way, I think this will give you the upper triangular version of L, but it hardly matters. So you do this once. Okay, and the cost on this is n cubed. Is that the comment? I think it is. Okay, there. Okay, that's an n cubed thing. Okay, so for 3,000 by 3,000, there will be a macroscopically visible delay when you do this. Okay, if I then do well, let's see how I can do this. You have LL transpose equals A, so A inverse B is L minus T L inverse B. Is that right? Yeah. So here's ready for my code now. If I do this and store L, anywhere else from now on, if I want to solve AX equals B, I can do it super fast like this. Let's see if I can get this right. There you go. I can execute this anywhere I like with different B's, and it will execute super fast, n squared. Do you see why? The reason is, I mean, there's a lot of interpreted overhead, so the whole thing, I mean, there's a bunch of stupid overhead. Basically, it looks at this. I mean, this is the formula for that, right? So it looks at this and it says, okay, let's look at L, and it looks at L and it pokes around for a while, and after a while it says, say, L is lower triangular. Oh, okay, I'll call the back solve instead of doing blah, blah, instead of factoring it. It's already factored or something like that. So it'll do this. Then this will be passed to this thing. And it'll look at that, and it'll analyze the matrix as if it's never seen it before, and go, hey, wait a minute, that thing is upper triangular. Oh, okay, I'll just go ahead and call. By the way, all of this thinking and takes way longer than to actually do it, unless the matrix is a couple thousand by couple thousand, right? So then it's fine. But the point is that this will now execute very fast. So I think I just answered your question. Okay. All right. So let's back to block elimination, which is what this is called. So what you do is you form A11. Actually, the comment I just made is very important because it's about to come up right now. So these two you would solve by factorizing A11 once and then back solving on A12 concatenated with B1. So this line would translate into a very compact thing. Okay. Then you form the Schur complement. Now to form the Schur complement, the point is here is you've already calculated these columns. So this is just a matrix multiply here and a subtraction. So you form the Schur complement, and you'd form B tilde. That's this right-hand side guy here, this guy. No more, there's inverses appearing here, but you've already calculated these sub-expressions. So this is fine. Then you determine x2 by solving this equation. That's the Schur complement times x2 is B tilde. And then you get x1. Once you get x2, you go back and you replug x1 from wherever our formula was. Here it is, right there, from this guy. Okay? Now the interesting thing here is you have to do the following. You have to solve A11 x1 equals this. But guess what? A11 you already factored on step 1. So this last step, step 4, is actually a back solve. It is not a factorization. The back solve. Right. So actually these are very important things. Yeah.
Why does the Schur complement arise? Like, what's the common thread?
It's
not. Is it just coincidence, or is there like
no, it's not coincidence at all. No, because yeah, there's a physical reason for it. It has lots of. I think you did a homework problem on it anyway. I think it comes up when you solve one set of if you have a block set of equations and you solve one in terms of the other. That's basically where it comes up. So, and it comes up in a lot of physical things too, like in networks, and it just comes up all the time, all sorts of things. PDEs, it just comes up everywhere, basically. So whenever you have some linear system and you impose some boundary conditions on some of the variables, a Schur complement's going to come along. It comes up in statistics too. I mean, this happens to be this is the error covariance of estimating x1 given x2 or the other way around. Do you remember which it is? One or the other. If I have a Gaussian joint variable and I estimate x1 condition, if I look at the random variables conditional expectation of x1 given x2, and I look at the conditional covariance, it's this thing. So it just comes up everywhere. So, okay. All right, so if we work out this block elimination and see what happens, you have a big drum roll and you work it out and you think it's all very clever. When you total it up, you get something like this. And we're going to do it in terms of factorizations and solves, back solves. You get something that looks like that. Okay? And we're going to assume, by the way, that the smaller system, the Schur complement one, we're going to do by dense methods. So to pay for the dense method, it's going to be n cubed. So you get something that looks like this, n2 cubed. You get this. Now, if you just plug in a general matrix A, it comes out actually not down to the leading order, but of course, as it has to be down to the flop. It's identical to what we had before. So there's no savings. There's absolutely no reason to do this. Well, sorry, in terms of flop count for a dense matrix. Now, the truth is, this is exactly how it's done when you do blocking and stuff like that. This is how you get fast. Because you arrange for, like, the Schur complement block size to be just right for your registers and your L1 cache and all that kind of stuff. And you'd get that size just right, and this thing will give you a big speed up. But that's a secondary question. Now, this is useful block elimination is useful exactly when A11 has extra structure that can be exploited. Okay? Now, that's when it does, this method is going to speed you up like crazy. So let's look at some of those. Here's an example. We'll do it a couple of examples actually, because they're very, very important. If A11 is diagonal, okay, that means that your matrix looks like this. I'm just going to draw, a pattern like that. Okay? If it looks like that, then you're going to do unbelievably well. And here's why. Let's just put some numbers on here. Let's put 10,000 here, and let's put 1,000 here. Okay? Something like that. Okay? You're going to do really, really well. So I have 11,000 equations, 11,000 variables, but it's blocked in such a way that A11 is diagonal. Okay? So, and by the way, this has meaning. This will have meaning in any application in which this arrives. It basically says there's 1,000 common variables, and everybody depends on them. Every equation, everybody. If you look at every variable, they all depend on those 1,000 common variables. But then there's 10,000 variables that don't depend on each other, and all I'm doing is I'm providing the English description of this sparsity pattern. That's all I'm doing. Okay? So if you see this, actually, from this class onward, if you see this, some big green lights should light up. This is what you want to see. If you see something like this, you will know this will scale to unimaginably large systems. Okay, and it'll scale very gracefully. Now the reason here is this. You just go back and look at what we're going to save, and we can actually even determine. I lost my algebra. Here it is, right here. All right, so let's actually see what happens in this case. A11 is diagonal. Well, this is like super cheap right here. That's again a non-issue. Don't even think about it. This, by the way, here's the joke. Forming S is now the dominating thing. So in fact, if you were to, the joke is in this problem, if you were to actually if you were to profile the code that solves this, you would find out that most of the time would be done doing matrix multiplication. It would actually be forming this. Okay, that's going to dominate completely, and in fact, it's going to be something like it'll be 1,000 by 10k by a 10k by 1,000 matrix multiply. That's it. At the end, you'll have to solve a 1,000 by 1,000 system, but that's going to be 1,000 squared, and this one was 1,000 times 1,000 squared times 10,000 is 10 times more. So we know exactly the number of flops it's going to take. It's going to be 1,000. It's going to be multiplying this matrix by one like that. That's it, and it will be seriously fast. If you were to take this and pass in a matrix like this and just write this backslash something, it's not going to work. I mean, it'll just sit there, and actually it'll very happily start factoring this. Very happily. This will not be recognized. This structure will not be recognized, and it'll start factoring things and things like that. And most of the time, of course, it's multiplying 0 by 0 and adding it to 0 and then storing it very carefully back and then accessing it again later, pulling it back in. But it's very happy to do so. No problem. It'll just do it. And it just will never finish. Okay? So, by the way, this is called arrow structure. So it's good. It's a good thing. So from now on, arrow. By the way, let's do another example. Suppose, in fact, this 10k was 10 1k by 1k blocks. Okay? I can't fit 10 in there, but you get the idea. Okay? By the way, there's a story behind this. Basically says I have 11 groups of 1,000 variables each. Okay? One of those groups connects to everybody. That's this last group. The other 10 only connect to that last guy. So, in fact, you should even visualize the following graph. Right? Looks like that, except there's 10 of these. Okay? So each node here in the graph is a group of 1,000 variables. This group does not depend on that one, but one of them depends on all of them. How do you solve this? By block. I mean, you do block elimination. This will be way, way fast. Because how do you do A11 inverse? A11 is 10,000 by 10,000. What's the effort to compute A11 if it's 10,000 by 1,000 blocks? How do you well, you don't calculate A1 inverse, sorry. How do you calculate A11 inverse A12? How do you form this expression? How fast can you, what's the cost to factorize a block diagonal matrix? Yeah, you factorize each block. So this is 10 times 1,000 cubed divided by 3. That beats like crazy 10,000 cubed over 3. I mean, by a long shot. Okay, so that's very important. Okay.
So is the moral of the story, don't use a backslash and just go through this algorithm with your own script?
No. Now I'll tell you a little bit about this. Okay, so having said all that, for this example, here's what would happen. So, okay, so let's talk practically about what would happen here. It would probably work if you had a matrix whose sparsity pattern looked like this. Okay. Okay. If you did this, now let me just explain a few things. If you just did this backslash b, too bad, it'll never work. And it's 11,000 by 11,000. Never, never. Okay. However, if you gave, say, MATLAB or some other system the hint that this was sparse. So by the way, if you say it's sparse, all you're saying is there's a bunch of zeros. There are a bunch of zeros. You see this is giant triangle here, giant triangle here. These are all zeros, okay? That's a lot of zeros. There's a lot of non-zeros, though, over here, right? But if you do that, then actually it is overwhelmingly likely that it won't do a bad job, because the method will actually get all of these guys first, and then in the ordering, you will get something. It might not get it exactly right, but it's likely to do pretty well. Because this, so in fact, this arrow structure is one that a normal sparsity handling system is probably going to recognize. Okay? So in this case, declare it as sparse, do backslash. You can do your own experiments, but they're not really very interesting experiments. They're just experiments on what some people implemented, you know, in Massachusetts. Or I mean, it's not that interesting, right? I mean, the important part is if you do real problems like this, you're calling these things directly. Then, of course, it's your job to do this. But now let me mention some others where it's not obvious. Okay? Let's do one. Here's one. Let's suppose you do medical imaging, for example, and suppose you do MRI or something like that, and you have to solve an equation that looks like this. Okay? Let's make this like 1 million variables, and let's make this 1,000 here. By the way, I have no idea what this is, but let's just imagine that such a thing is there. And this 1 million by 1 million here, if this was like diagonal, you know what to do. We just did it. I'm going to make this, though, a DFT. Okay? So it's a discrete Fourier transform. That's a dense matrix. Completely dense. So you can form, well, you could attempt to form your million plus 1,000 by million plus 1,000 matrix and actually attempt to solve it. It's completely dense. Everyone agree? Totally dense. Okay. No sparsity is going to help you out. The gods of sparsity, you are on your own on this one. Okay. However, how fast can you solve this system? By the way, you can't even store this, right? But all you have to store is this part, right? And this is pushing it, but you know, that's your fault for going into medical imaging. No, you do medical imaging, you're not gonna do this on something with a couple of gigs of RAM, right? I mean, obviously we can work out what that is, but this is perfectly storable. Otherwise, you don't store this block, you know, obviously. How do you solve this? Yeah, of course. So you look at this, at this and you go back and you say, well, what do I have to do? And you go, well, I have to calculate A11 inverse a couple of times. By the way, you do not solve a discrete Fourier transform equation by, you can't even form, if it's a million by million, you don't even form a factorization. It doesn't matter. You actually calculate by the inverse DFT. It's a n log n. So it's 20 times a million flops. It's way, way fast. Okay? Everybody got this? So this, by the way, these are not obvious things. They're known by lots of people, but probably more than an order of magnitude more people who should know these things don't know them. So that's why I'm telling you these things. So, okay, so this is very important to know. So in fact, I cringe whenever I hear people in very unsophisticated ways talking about, you know, scaling, and it's like, oh, I tried that. It's way too slow. Well, anyway, though, by the way, the difference between this and just typing a backslash b, the technical name for that is just typing a backslash. That's called stupid or naive linear algebra, and this is called smart linear. Smart linear algebra means you kind of know what you're doing and you're exploiting structure at this level. That's what it means. So,
how do you communicate sparsity to a computer in English?
How do you communicate it? Well, it will just end up being sparse. I mean, do you mean in MATLAB? How do you do it? There's a very bad way, and then there's a good way. You make it sparse in the beginning, and then it'll be preserved as you do the right operations on it. You have to be very careful in MATLAB because, like, one false move, you know, one little character here, and boom, you have a dense matrix. You add identity to it, you know. Now, adding identity to a sparse matrix, you get a sparse matrix, right? Not in MATLAB, you don't. So you have to know. Oh, you shouldn't add I, E-Y-E. You have to add spy or something. I don't know, S-P-E-Y-E. That would be the sparse identity. Right. Now, of course, that makes you wonder, under what circumstances is the identity not sparse? And I don't know of any. Maybe 2 by 2 case, because then you could say, well, only 50% of the entries are non-zero. I don't know. It's not my, I don't, but anyway. Okay. So I think that's it. So basically you want to look for things, block things. If you look at a block and you see a block that's easily solved, exploit it. By the way, if what's easy to solve about it has to do with its sparsity, you can just be lazy and let your whatever, do your offering to the gods of sparse matrix factorization orderings, heuristics for the orderings, and hope that it works. But if it's dense or something like that, you're going to have to do the work yourself. That comes up in a bunch of cases. One of which we're about to look at right now. But that's the idea. By the way, let's quickly talk for fun about some fast. What systems can you solve fast? I mean, we've already looked at some obvious ones. Diagonal, lower triangular. Oh, we just talked about one a few minutes ago. Block diagonal. How about like block lower triangular? Can you do that fast? Yeah, of course you can. Because if it's block lower triangular, you can do back substitution at the highest level or whatever, and you'll have matrix inverses to do on the blocks. Okay? We talked about another one, FFT. Sorry, that's the algorithm, DFT. So discrete Fourier transform is the operation. FFT is an algorithm which does it fast. Others would be things like DCT, so discrete cosine transform that you'd use in imaging. Anybody know others? They're fast? Which one? Toplets, yeah, Toplets is a good one. So you have fast algorithms for Toplets matrices, and they all have names. And usually people are tortured by having to learn them every operation by operation. Like Levinson-Durbin is one of them. And do they teach us in statistics? Probably. No. Okay. Good. Fast. Oh wait, it doesn't matter. For Toplets, no. Okay. Hunkel matrices is another one. So those go like this. Circulant. Yep. Circulant. How fast can you solve a circulant? N log n, right, because you take an FFT, multiply FFT back. So that, and circulant, of course, is the matrix, is circular convolution. Convolution, well, that's Toplets, we already covered that. There's a bunch of others, and it's fun to actually poke around and learn about others. Like there's one called the fast Gauss transform. That comes up in machine learning. That's like way fast. So there's a bunch of them that are like order n. There's some other ones that they're whole fields that can be described as fast methods of solving AX equals B. For example, if you solve an elliptic PDE, you are solving a very specific AX equals B. Okay? And those can be done like, some of them are like, they can solve it insanely fast. It's not easy to do. It is not trivial. But for example, if you go to someone and say, oh, I have this grid, like I have an image, let's say. Right? For example, you suppose you have an image, and all the constraints only connect a pixel and its immediate neighbors. And you say, I have to solve a set of linear equations that looks like that. It'll have a very characteristic look if you look at it. It'll be like stripes and things like that. And if you do PDEs and things, you'll just immediately say, okay. But in fact, solving that equation, that's your 1-1 block in an image. Let's do the image you're doing or will do or have done. In homework 7. What are you doing now anyway? 6. Oh, well, that shows you what we're thinking about. All right, so suppose we scaled it up to 1K by 1K. So you have 1 million variables. Actually, at each step in that algorithm, the 20 steps, you will solve, I promise you, a million by million equation. Definitely. But it's super duper sparse, right? Because each row and column will only have like 3 entries. Because you're connected to yourself. You connected 4 entries, whatever. You're connected to your neighbor above, below, left, right. So super sparse. By the way, sparse orderings won't do so well. It does okay for your homework, or it should anyway. It does. But it won't scale to bigger numbers very, very, very gracefully. However, if you look at it carefully, you'll realize that in fact, solving that set of equations, that big A11 block for that problem, you know what it is? Solving an elliptic PDE on a uniform grid. Then you go to your friends. Or it's like a Poisson equation or something like that. So you go to your friends who know about PDEs and you say, how do you solve that? And they fall down laughing. They're like, are you kidding? 1K by 1K? Oh, we precondition blah, 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 Fourier transform, multi-level. I mean, whatever they do, there's probably some people here who do this, okay? It's not easy. It's a whole field, right? But the point is they know how to do it. And then you, after they calm down, you say, great, could you just give me the code that solves that? And then wherever you have to do A11 in the back substitution, you put that there. Now you're done. So, okay. Yeah, that's enough on that. Let's look at a consequence of this. It's the idea of a structured matrix plus low rank. This is actually very important. This is also extremely good to know. And this is something that you have to do. In other words, you better recognize this because no automatic system can do this, period. So you have to do it. So here it is. Suppose you need to solve a plus bc times x equals b. Now, normally, b and c are small. So you're supposed to think of b, this is low rank, this is like rank p. B is a skinny matrix, c is fat, and a is something that's quickly invertible. A could be the identity or diagonal, block diagonal, lower triangular, you take your pick. Could be solving a Poisson equation. Doesn't matter. It's something you can do fast. Circulant, who cares? Okay, and you want to solve this equation. Now here's the problem. Generally speaking, whatever structure was good about A is almost certainly destroyed by adding, in fact, just add a dyad. Just add a b, little c to it. And it'll destroy anything. Of course, it'll destroy a DFT matrix, a DCT matrix. Toplet structure is totally blown out of the way. Diagonal, forget it. You make an outer product, it'll spray non-zeros everywhere. A block diagonal ruined. So, that's kind of the idea. Okay. By the way, once someone calculates this and hands you this matrix, all over. You can't, if they don't tell you it's A plus, once they multiply this out and hand it to you, it's all over. You'll never recover. You'll never get any speed out of it or anything. You're stuck at n by n now. Okay, so let's look how to do this. What you do is you do what we did in duality, which is you uneliminate. You introduce new variables. Strange. So here's what you do. You uneliminate. You write this as ax plus b times cx, and you introduce a new variable called y, which is cx. You uneliminate. Then you write this as ax plus by equals b, and then cx minus y equals 0. That says this is y equals cx. So if you can, these two are completely equivalent. If you solve one, you can solve the other. Okay. Now, when you look at this, you should have the following urge. You should look at a matrix like that, and your eye, don't ignore this. Your eye should gravitate towards the minus I. You should, well, yes, that's right. Okay, sorry. Your eye should gravitate towards this minus identity. And it should look at that. And you should have an overwhelming urge to carry out block elimination. Because of matrices easy to invert, they don't come simpler than I, right? So you should have an overwhelming urge to eliminate this. By the way, if you eliminate this I, if you eliminate this thing, what will happen? You'll get the sure, you go like, oh my God, it's my great, this is fantastic. That's an I. I now know that if I see an easily inverted matrix appearing as a block in a diagonal, I know what to do. You do it, you'll form the sure complement. That's the sure complement. Okay? So by the way, if the I were huge and A were small, great. But of course, this is still, so if you eliminate this block first, you're actually back where you started. So that now the trick is, so you have to actually hold off on the urge to eliminate an easily inverted block. You must hold off. This is very important. And instead, you eliminate A. Okay? So that's the idea. And actually, let me explain the reason. The reason is this. In this application, I is small. This is, let's say A is 1,000,000 by 1,000,000, but B and C are each, 1,000,000 by 10. And 10 by 1,000,000. But anyway, that's what they are. In that case, this I is 10 by 10. So it doesn't really help you to eliminate this. It's this 1,000,000 by 1,000,000 guy you want to go after. And A, for example, could be a DFT, a discrete Fourier transform, right? Or something like that. That's the one you want to go after. If you eliminate that, you get this. I plus C A inverse B times Y equals this. And this allows you, this we can actually handle efficiently. Why? Because you put A inverse B here. That's fast because somehow you have a fast method for doing A inverse. You form in this case, you form the smaller one, and then you solve that. And then this is sometimes written, this has got lots of names. It's called matrix inversion lemma, but it's got lots of other names. If you're British, it's called Sherman, Morrison, Woodbury, and then any subset of those, depending on if you went to like Oxford or Cambridge or something like that. Okay, so that's one, and it's also called let's see, matrix inversion lemma, Sherman, Morrison, Woodbury. There's one more. I think it's if you came from MIT, there's some name you have for it, special. It doesn't matter. You'll hear another name for it. So what's it called? Well, anyway, I don't know. I'll think. It hardly matters. The point is, you'll hear lots of people talk about it, and it's sometimes it's just written out as this formula: A plus BC inverse is equal to this, assuming all the inverses here, A is invertible and A plus BC is invertible. You get this formula, and you would see this. I mean, here are the types of things you should know. It's a staple in signal processing. In fact, essentially, most signal processing relies on this. This is basically the one non-trivial fact of all of signal processing up to about 1975, I'd say. It's just this. Same, by the way, this is also the trick for optimization. So let me explain what it is. In that case, B and C, I mean, the most classic case is something like this: diagonal plus low rank. So here, well, I can't use lower B. So PQ transpose. There you go. So suppose you need to solve that, something like that. So diagonal plus low rank is a beautiful example of a matrix that if you know what you're doing, you can solve equations of diagonal plus low rank so fast it's scary. But if you don't know what you're doing, it's a total disaster. So this one you can solve. It's actually, in fact, what is the order of solving that? Order n. It's just order n. There's nothing here to do. It's just order n. So if someone says, don't you understand I have to solve a million by million equation? And you go, yeah, I understand. And they go, it's totally dense. Dense. Million by million. That's like 10 to the 12 entries in my matrix. And you go, yeah, I know, but you can solve it in about a half a second, maybe less. Okay? But you have to know what you're doing to do this. Okay? Nothing will recognize this. By the way, you might ask, is it easy to recognize a matrix which is diagonal plus low rank? Because if it were easy to recognize, I guess you know the answer, by the way, I'm asking. But if it were easy to recognize, you can imagine some processing or some higher level thing that would look at the matrix. It can think a while. If it's a big matrix, it might be worth thinking. So it could look at it for a little while and go, whew, look at that. You're lucky. It's diagonal plus low rank. Oh, good. So what do you think? Is it easy to determine diagonal plus low rank? No, it's a famous problem in statistics. It's in comes up in lots of areas. It's impossible. Okay. Let me just ask this just to see if we're on the same page here. How about this? How about alpha I plus PQ transpose? I think, is that right? Am I asking the right thing? I think I am. All right. By the way, I'm not sure I know the answer to this one, but let's try it anyway. What I'm about to say, my example might be just for symmetric, but let's just try it anyway. How about a multiple of the identity plus rank 1? Can you detect that in a matrix? How?
Eigenvalues of the matrix?
Okay, fine. Eigenvalues will do it. Thank you. Thank you. What are the eigenvalues?
One eigenvalue and all others are.
You got it. Okay. And that's if and only if, right? So, in fact, this we can determine. This we can determine. Okay? Because one eigenvalue will be different and all the others will be equal to alpha. Okay? Yeah.
Problem one of the toughest for a big matrix. Yeah.
Correct. Right. So then we say, fantastic. We have a method of recognizing a multiple of identity plus low rank. Okay? And we have to calculate, all we have to do is calculate the eigenvalues. And what's the cost of that? N cubed. Actually, with a multiplier that's about 5 or 10 times more than just solving the stupid equation. So, okay. So, all right. But that's, well, but it had us, I mean, the main thing here is to think. But diagonal plus low rank, forget it. So, okay. So, all right. So that's the picture. And these are just sort of stunning. You get stunning speed ups if you know this material. By the way, I should say I went over this kind of fast, and A slightly less fast description is the appendix, which you should definitely read. And we're going to assume, moving forward, that you've read it and got it. A lot of this, by the way, you can experiment with. I mean, you can experiment with it in MATLAB. You have to be careful, though, because you're kind of experimenting half with, half of it is this method and half is what MATLAB actually sort of does, and stuff like that. So, okay, so I guess we'll quit here.